where we've been undertaking quite a significant amount of OLE work and modifications for, well, I guess kind of the last 2 years, really, 3 years. So yeah, we're going to talk to you today about Colton Junction and the tangential wiring works that we've undertaken and the process we went through to kind of get from initial early design all the way through to it being entered into service that it is today. So just quickly to give you a kind of overview of the TRU programme and the alliance that we work in. So you can see there that we've got 3 kind of alliances delivering the programme of work across the whole programme of TRU. So we've got TRU West, TRU Central, and then TRU East, which we're involved in. So TRU East runs from Leeds all the way through to York, and we're electrifying the whole of that route, and quite a significant amount of work. So it's 25 kV AC electrification between Colton Junction and Leeds. Line speed increases through to 125 mile an hour. So on the down and the up and down Leeds lines, from Copmanthorpe level crossing through to just north of Church Fenton station at the moment, and then those line speed increases move forward as part of later commissioning stages. Re-signalling to improve capacity and allow for line speed increases as part of the line speed increases. So closure of level crossings, over bridge and under bridge reconstructions, culvert and drainage interventions. You can see there 3 new culverts that we installed on the knot lines, and then a new electrified depot at Shipley, and that's like a real enabler for the works that we're undertaking at E2, where we remodel the Neville Hill area and the cutting there, and when we undertake new OLE works. So we need to get the Shipley depot electrified and sort of in service for kind of 6 months and operational, so Northern can have their fleet there before we close Neville Hill, that area, for 12 weeks when we do that big remodelling stage, which is EIS-V and EIS stage Y for the OLE work. So I'm going to hand over to Matt, who's our OLE SPE for Network Rail, working on the project. We're going to go through some of the design elements for Colton Junction.
Thanks, Luke. So project E1, this is the electrical sectioning diagram for the E1 footprint. We've electrified between Colton Junction and Church Fenton, 4-track railway. We've got 3 crossovers in there, a number of bridges, 1 station, Skelf. The top 2 roads are the up and down Leeds, the bottom 2 are the up and down Normanton's, and the Normanton's interfaced with the East Coast Main Line at Colton Junction. So we've introduced 32 STKs of new electrification using the Siemens range of cantilever equipment. It's fed via Colton Junction MPTSC via Hamilton feeder station. We've got the future section sites shown in cyan there, and also a Cairo neutral section, which is adjacent to Colton Junction. They're not commissioned yet. We don't need those until E234 come online. The Cairo neutral section is more or less fully built and tested. It's jumping out at the moment, so it's essentially just 3 back-to-back insulated overlaps. Again, we don't need that electrically until E234 come online. So Colton Junction itself sounds like a lot of you know about it anyway. So it's southwest of York, off the East Coast Main Line. The photo there, you see the Leeds lines are just straight through. It's the up and down Normanton's that are interfacing with the East Coast Main Line at the junction itself. It's key to complete the overall TRU West to East upgrade works. We need to get off TRU and onto the East Coast Main Line and off to York. It's an equal split, 125 mile an hour high speed double junction. It's where the Selby diversion joins the York and Normanton lines. It was electrified with British Rail Standard Mark III BOLE in 1989. Probably the highest speed double junction in the UK, a real one-off. We will have wired, junctions in the past, but not at this, high speed. So the existing wiring arrangement, it was wired with overrun protection down the Normanton's and the Leeds lines, and also future extension to Leeds. It's headspan construction, which we touched on earlier. So using span wire structures, not portals. The issue with headspans is they're not mechanically independent. So if you have a problem on one line, it will generally affect the adjacent lines as well. Turnouts and switch diamonds are all cross contact bars. We can see circled in red there. Electrical sectioning in the junction is via a section insulator. You should never have seen a pantograph because it's overrun only. The APCO system would have dropped the pantograph further towards York as the train's heading down the Normanton lines. Section insulators are hard spots in the OLE system. They're not suitable for 125 miles an hour. We don't really have any of that are rated to 125 either. And SIs require more frequent maintenance than the preferred alternative, which would be an insulated overlap. Obviously something we need to factor in when we're considering getting in and maintaining in this junction area with the limited access we've got. So this is the existing wiring schematic, simplified. You can see the wires crossed 3 times there, using cross contact bars circled in red. We've got the SI in the middle for sectioning, circled in blue. There's also a low footbridge people like to stand on and look out of, which is restricting the wire heights. So the contact wire, the contact wire through the junction was in graded contact wire because of that footbridge. All routes 125, the down Normanton's actually 100, but in essence it's just high speed everywhere. So what's cross contact wiring? In a nutshell, the wires just cross each other. The main line's always the lower wire. The higher speed route takes priority. That's because the slower speed route will sit on the upper wire, and when it interfaces with the lower wire, it's going to sort of crash through the lower wire. But because it's slower speed, it's lower pantograph forces, so it's acceptable. The 2 wires are physically connected together via a cross contact bar, which is that diagram there. That allows both wires to lift simultaneously together, managing hookover. Hookovers where a contact wire can end up underneath the pantograph, and you can end up dewiring. Cross contact bars are also generate high pantograph forces if poorly designed or maintained. It can become detached, potential dewirement, and as Colton is high speed everywhere, there's no route that can actually be biased. So the modern way to wire crossovers and turnouts is tangential. Just means the wires don't actually cross each other. It's standard UK Master Series arrangement. There's no cross contact bar. Hookover is managed by cross droppers. So if you look at that diagram at the bottom there, when the pantograph's on the left-hand contact wire, the pan lifts that wire, it unloads the catenary above it. That in turn is diagonally connected to the right-hand wire, which lifts at the same time. Both wires then land on the pantograph at the same height, and they don't ride on the horns. And it's much softer system and lower forces than a cross contact arrangement would be. But you do still bias the main line 20 mil lower and sacrifice performance to the slower turnout route. It's the preferred arrangement over cross contact. So electrical sectioning, which we needed in the junction, you could do it 2 ways. You can either do it by a section insulator for an SI or an insulated overlap. The insulated overlap's the preferred method because SIs they can generate higher higher pan forces and damage the pantograph. They need more frequent maintenance. An issue just getting access in that junction. No weak link, dewirement risk. There's nothing actually approved for 125 anyway, so we would have had to go down a product approval route for that. One benefit is they are reasonably short in length, around 6 meters. That's why we use them in sort of short crossovers, and you'll see them kind of everywhere. But they won't be in a high speed route. So the preferred way is an insulated overlap. That diagram on the bottom. It's reduced maintenance. It's just normal wiring maintenance. Approved for 125, will be much longer, but 40 meters. And you can see the red wire is in running, and then it anchors off in the cess, and the blue wire comes in, and that's the changeover point. It's just wires. It's not a heavy piece of kit like the SI. So we looked around for standard general arrangements to use, and there weren't any for this high-speed switch diamond. One was available in the Series 1 design range, which was used on GWEP. However, it still used a cross-contact bar, and it was just for a much lower speed in general. That's the schematic at the bottom left there. You can see the diamond highlighted in red. The sectioning is the blue diamond, SI or overlap. I think you get the in a slower speed crossing like that. An SI is only going to fit. However, at Colton Junction, the S&C is physically longer than normal for the higher speed, which is going to be an advantage for fitting in an insulated overlap. So this was the final proposed wiring diagram based on UKMS principles, full crossed, tangential, cross droppers shown in red there, SI replaced with a insulated overlap circled in blue. All the wires at the same height, although it was graded because of the bridge, because we couldn't bias one route over another. And industry best practice tells us this should have been the correct solution. So the Form A was progressed on this basis. We also replaced all the headspans with portals, so the equipment was more mechanically independent. We renewed aluminium catenary with copper, renewed junction cantilevers with nice new shiny Siemens, and ensured no contact wire splicers were in the junction itself, because they're also a hard spot, high forces, high contact wear. The approval in principle was accepted on this basis. Still concern over forces, but we could verify these by dynamic modelling. Modelling's not new by any means. The TA use it a lot to verify different concepts they're working on. Huddersfield University are a non-resource, so we approached those guys, got them contract. And that's the wiring model there, just an example of Colton Junction itself, actually, what it looked like in the model. You can see the contact wire catenaries and droppers, and how they would model the pantograph, the figure 8 on the left there, as a spring mass damper system. See you over to Stuart.
Thank you. So I got involved at the Form B design stage. So as Matt showed a simplified diagram there, you can see there an extract of the layout, kind of what that looked like. So I suppose we applied that logic of the cross contact, removing the cross contact bars, putting in cross droppers, and putting in the overlap. It's what you can see here. So we've now got an insulated overlap in here. Got the tangential wiring we talked about in the three pieces of S&C that you can see. So we had to provide this design to the University of Huddersfield, give them all the inputs required for that to allow them to represent what this looks like in a computational model. And then we analysed 3 different routes here. We didn't analyse the up main route, because that's a standard turnout going from the East Coast Main Line towards Doncaster, so it's not seen as deemed as special or anything different. Whereas the other 3 routes, you've got multi-wire interaction in a negative way. You've got an additional wire coming into interaction with the pantograph whereas you don't have that on there. I think there's a couple of things to talk about on there. We looked at the stagger design and refined that to manage head roll as well, which is something we haven't talked about previously. So if we look at that, what you can see here is some exaggerated images of what that means. So as a wire's resting on a pantograph and that's traveling at speed, the pantograph will naturally tilt to the side of the wire that pantograph is. The pantograph will tilt to the side that wire is on. We call this head roll. This is exaggerated, as you can see down here in the bottom left. And obviously, we can design our staggers to allow the incoming wire to come onto the pantograph or accept that incoming wire a bit better. And obviously, that manages the hookover risk and also the forces that you'd be generated within that interaction. Call it encroachment. You can see at the bottom now we've got a picture of a pantograph with a tilted head, and you can see that it's got a separate spring system that rotates that pantograph accordingly. So to just explain what that looks like, if you've got a single wire running on a pantograph there with the uplift shown, then because the wire's on the left-hand side of the pantograph, the pan will naturally tilt left. Obviously, we've got uplift occurring there. It could be 100 mil. So although we can design the wires to be perfectly level, your red wire will generally be higher than the green wire. We then get to where your cross drop would be, and as your red wire is uplifted, that uplifts the catenary wire as well, which then lifts the green wire up and over and onto the pantograph. So it should come to rest on top of the pantograph carbons, and then one of those two wires will come off slowly after it's stabilized. So the initial scope we gave to university was to look at those routes I've talked about. So you can see that a bit clearer with the down Normanton down main route, a single wire with an additional wire coming into action from the down main, and then the up main up Normanton route where you've got multiple interactions between the down main and the insulated overlap, and then the down main route which goes over the diamond and then interfaces with the down Normanton. So we obviously need to look at what trains would potentially run in there. So what you can see here is the scope that we picked up out of 27715, the standard for network rail OLE design. And what that suggests is these configurations, so two pantographs with these different types of pantograph head, what those spacings may be, and then also the speeds that they have. And you can see that totals 20 configurations, and then we're running that over 3 different routes. So that's 60 configurations or simulations total that are required. Okay, so they ran that after we gave them all that information, and as you can see here, the limit of the force that a pantograph should be allowed to accept is 350 newtons, simulated by the top of that line on those two graphs. And then the figure on the left is showing you the pantograph force in pantograph 1, which is obviously showing it compliant from force, but you can see there is some loss of contact because we're below the 0 at the bottom. But then the pantograph on the right there, you can see circled at the bottom, we've got a 1.4 kilonewton force, which is 4 times the allowable limit. And that could potentially damage the pantograph either, but it should need to be replaced, or potentially break that and then dewire the whole junction. So obviously it wasn't successful in that first process. That we looked at there was the down main down Normanton route. So if we're looking at the bottom track from the start from the right hand side, a train's travelling right to left. It's running on a single wire underneath a really low footbridge. It then has 2 wires come in for the up main up Normanton route. You've got the up main wire run coming off and leaving that pantograph. You then go through the insulated overlap, so you're going from 1 wire to 2 wires back to 1 wire. You then go through the diamond junction where you've got going from 1 wire to 2 wires and then back to 1 wire again. So that all happens over 240 meters, 125 miles an hour, which is 4.4 seconds. So there's a lot going on that pantograph's seeing. So the first one was obviously compliant, but the second one, because that's happening so quickly, the wire's then bouncing and the second pan hits that and the forces are very, very high and created lots of concern. So we had to go away and look at what do we change, how do we make this better. It's key, we had to fix that. So the first thing we looked at was the train configurations stated in the network rail standard. were they actually expected? So the figures I showed you there with the 1.4 kilonewtons wasn't actually the worst. If we did run an 8 meter spaced freight electric freight unit, it was 2 pounds within 8 meters. That was 2 kilonewtons force within that. We quickly identified that wouldn't run on the route, and therefore we said we should probably understand what configurations the pantographs will run and at what speeds and on what lines. And the other things we looked at was lowering the wire throughout the junction, because that creates a softer system, obviously with longer droppers within that, and then removing some gradients. Obviously the bridge was there, which is why we had wide gradients through, and then we're trying to remove that accordingly. Okay. A greater review of kind of what the pantograph sees as well. So Matt spoke earlier about not biasing a certain route, but it became clear that that actually what's the pantograph seeing when you look at it on each individual route, that may change. So we'll look at that further in a second, where we introduce some half cross droppers and wire hog. And then we also, because the insulated overlap was kind of the root of all of our issues, we looked at whether we could remove that. Obviously significant issues if we did. And then some wire damping as well. So how to make that second pantograph perform better by trying to slow down that wire bouncing up and down after the first pantograph's passed. So if we look at the switch diamond in detail, it's a bit clearer to see. That's what it looked like. If you look at that route signified by that yellow arrow, you've got a pantograph travelling on wire run 70 there with a single wire on, and then 69 is obviously needing to be lifted on top of that pantograph as smoothly as possible. And then as you go through, wire run 70 slides off the edge of the pantograph and wire run 69 remains on it. That's on that route. Again, look at the other route. We essentially have exactly the same issue. So you've got wire run 70 being ran on, wire run 69 needing to be lifted on, and then wire run 70 sliding off afterwards. So what we've done here is, you can see by the CD1, CD2, CD3, CD4, is put in half cross droppers to manage that accordingly. So we've only cross dropped it from wire run 70 onto 69 to lift wire run 69 onto that pantograph. And then because 69 was always the wire we're running onto, we can bias wire run 70 to be lower to mean that the wire run 69 is accepted more easily, which went against our original thinking. The other thing I mentioned was the wire damping. So in an insulated overlap, as Matt showed you earlier, we had two structures 40 meters apart where we support different wire runs, and then your pantograph transitions from one to the other. We actually introduced a third structure in the middle to split that wire run or that span in half, and we registered that. And what that did, we quickly proved, was dampen that wire down quickly because it changed how that system performs. So there's a bit of a learning curve within all this. As allocation designers, we generally like to use general arrangement drawings and then place them into service in a bespoke arrangement. I always like to use the example of we've got the jigsaw pieces, but we're trying to paint a different picture. So yeah, UKMS models. UKMS had been modelled by the University of Huddersfield, but it had been modelled each discrete kind of interface, so a crossover, a turnout, an overlap. Had any of those things been analysed, all happening within 240 meters? The answer quickly became no. And then I think the University of Huddersfield will model it. We're used to modelling those kind of features, but not, again, all happening very quickly. So there's a big learning curve between us and them. So for example, they didn't use to model a full pantograph head. They only modelled the width of the carbons. It became clear we need to do a bit more than that to make this work. Touched on that, our understanding there, and then allocation designers, kind of what we do. So we learned quite a lot about what cross droppers do and why they're doing that. So I think we've probably challenged some UKMS general arrangement drawings now in maybe oversubscribing some features in over a headline, and that's because depending on which way your crossover's running, it potentially doesn't need to have cross droppers at both sides. So on the modelling configurations, here's two big tables. The one on the left gives you the pantograph configurations, the lines, the spacings within that, whether it's a single pan or two pantographs, what line speed they can run at, and then what routes that they can run on as well. So that came from our review of rolling stock and also the section appendices. steps, compatibility, and so on. The right-hand side then looks at every configuration of the model we looked at, so lots of optioneering to try and get the best result. So you've got 69 pan configurations and 23 models of the OLE design we had, which gives you 1,600 simulations. So these simulations were taking hours and hours to run. They're running them overnight at the university on the supercomputers, so we obviously couldn't carry out 1,600 simulations. So we had to quickly find the worst performing configurations on each route, and then kind of analyze each of those models against that to give us the best performance. Here we go. So the results of the final model on the left-hand side, you can see the worst performing pantograph was 188 newtons, and then on the right-hand side, you've got a lovely video of what that looks like once the university brought that to life. So you can see different routes, single pantographs running, how the wires are bouncing up and down, how if you've got twin pantograph, as you can see there, the second pantograph is hitting a wire that's already excited and was giving us all those issues. Very expensive video. Okay. I suppose it did turn into a bit of a science project. It was really, really difficult. We learned lots of new things, but all the time we had to think, how does someone build this? And then also, how does someone maintain it? We were being so specific in what we were modeling to such a great detail. So how do you ensure that this not only can just be built on day one and run smoothly on that first day, but then how does someone maintain that for the next 80 years potentially? So some considerations we had was wire gradient. So I talked about the lifting one wire higher than the other. We actually, rather than hogging it, that gave us better results. We graded it in and out, and we did that because it's a more standard arrangement. So from a dropper in perspective in the future, if you needed to adjust anything, it's standard. There's nothing bespoke within that. The cross dropper position and tolerance. You generally, on a layout plan, you just see a big cross, and that tells the construction team to go and install a cross dropper and they work out the positions of those. We were positioning cross droppers in the model to millimeter accuracy, obviously. So you can see here we've listed each cross dropper there, what that position is, given that to the nearest 10 mil, and then also stated which wires they go from and to, because we've got half a set of cross droppers here rather than a full one. The other thing we looked at was dropper installation accuracy. Again, we've modelled this to perfection. So how do we ensure that it's built to that accuracy, but not only built to perfection, what tolerances and where those tolerances probably can be. We know where the risk is now. So we've specified there how accurate the contact wire needs to be at each individual dropper. And then we also kind of increased survey data throughout that process as well while we were designing. I'll pass on to Mick.
Yeah. Okay, so design came to construction. So how did we build it? We obviously knew we had some challenges in here. I think we all knew it was a critical junction, and consequences of failure here. We had, potentially high financial cost of train delay minutes, but reputational damage for ourselves and the programme and the electrification industry as well. So we wanted to make sure we got this right. Works were obviously required, which were quite complex as well. We had quite a bit of stuff to do in there. We had new structures to go in. We had wire lowering to do. We had multiple cross splicing to do of the wire runs. We had wire replacements. We had redundant equipment to come out, and obviously we had to hand this back after every shift that we went in there at works as well. So back to electric traction. So we really had to think about how this was going to be staged. So we also had limited access. So rules of the route access in here, we're talking by the time we get there between 1 and 2 hours working time. So you don't get much time in there, and that's once a week. So originally we planned to use 3 disruptive accesses, 54 hours. But first one of those, we were planning to go in and do as much enabling work as we could do. So getting the structures in, getting as much SPS up as we could do. Second one, we were going to plan to do kind of the technical bit, all the cross splicing, and transfer to the new structures. And then the third one of those was kind of a tidy up where we go in and replace all the wires. So we actually lost 2 of those disruptive accesses, which was quite a challenge to us. And it challenged us as a team as to how we kind of rework the plan as well. So as well as that, it's a very small footprint. So we've obviously got a double junction in here. There's a DNO crossing in here. We've also we knew the works needed to be carried out sequentially as well. So it really restricted the amount of yellow plant that we could get into a very small area. So it meant that we couldn't just increase the amount of people that were in there to get this delivered. Okay. So finding the solution. So we knew that because of the complexity of this, we weren't going to find a solution just receiving a design and the construction team working out how to stage this. So we got a workshop together between ourselves and the designers and the PEs, and we had to work really closely together to work out exactly how we were going to do this. So we challenged the scope. There was elements in there that we thought were unnecessary and we could take out, but we also balanced that with trying to deliver a better product. So there were splices in wires there that didn't need to be there, and we thought that by staging the work slightly differently, we could take some of those out and leave something slightly better for the maintainer. So because we've lost access in rules of the route as well, we looked at how we brought some of that work into rules of the route access. So obviously very small timescales in that access. One of the key examples was we did headspan conversion in there, and that was all delivered in rules of the route access where we only had 2 hours working time. So we also did other little bits and pieces in there as well, such as we'd had cloud point surveys, which allowed us to go in, install SPS, and then adjust that SPS so we knew we were going to the blockades in a much healthier position. So due to the complexity of it as well, and the amount of work that was going on within each of the disruptive accesses, we knew it was very hard to communicate to the site teams exactly what we wanted them to do. So what we did, we actually refreshed the design between the disruptive possessions as well. And we produced construction staging diagrams to try and explain that. We brought them to the working group, and we decided it was a good idea to bring those into the design as well. So that's what we did. We can see an example of that here for one of the stages. Very simple wiring diagrams, and it walked the site guys through exactly what the wiring looked like at every stage. So it was much easier to communicate that to the team. And then because of those changes as well between the designs, it gave us an opportunity as well between those disruptives. So we actually went out, did point cloud surveys, like I said, to go and look at things like drop tube positions, so that we knew that we were going in a healthy position, and we were doing the minimum amount of work that we needed to do in those disruptive possessions. Okay, so the delivery of the works. First disruptive possession was actually cancelled. So we started to look at doing the works in rules of the route. So we pulled out of those disruptives the portal installations, the TTC installs, the headspan conversion, and all the drop tube installations. So as much SPS as we could get up. That took us into our first blockade. So main works in there, we were lowering all of the wires across the junction. So that was grading in and out of that area. we cross spliced as well. So we actually tangentially wired the first 2 turnouts within that possession. And then obviously there's all the panning and insurance to get that handed back. That was meant to lead us into a 54-hour block a few weeks later, which should have been us kind of doing the majority of the remaining works. That was cancelled as well. So once again, we ended up back in a situation where we had a bit of time to have a look at how we de-risk that next blockade when we could get it rearranged. So we looked at little bits and pieces that we could do. We got the drop tubes adjusted. We went in there, we looked at any referrals or snags that we already had, identified those, got them closed out, as many as we could. We got all the cantilevers up in the air in those rules of the route blocks. We registered them and we took them down. So we knew when we went back out and put those up, they were in a pretty good state to final register. So that led us into our final block. So the last of our blocks, we actually did the cross splicing of the diamond, quite a complex cross splice. Got rid of the old section insulators in there. We replaced contact catenary wires, and then obviously we had to get it all handed back as well. So construction planning. So this is kind of how do we deliver the message to the teams before we went out. So obviously the usual thing, we put the hour by hour programs together. That went through the QSRA process. So we then took that plan to we had internal construction management and engineering meetings on a weekly basis. We picked the plan apart and we tried to de-risk everything we possibly could in those meetings. We made sure everything was ready, all the materials were right. We also started pulling together a presentation in those meetings for the site staff as well, just to make it even more clear. Not all of those guys are going to have a design in the hand, so we wanted to make sure the message was really clear what they were going to be doing. So in that presentation, we looked at the constraints of the site, we looked at the risks, and so we've got an example there. We got some of the risk assessment, parts of the risk assessment for the DNO in there. We also looked at things like rigging techniques, because some of the rigging was quite complex. We put diagrams into the guys as well, so they knew exactly what they were going to be doing in those ships. Okay, and then coming towards the end, assurance. So I suppose what made it a success was the way that the guys were organised getting to site, but then being able to hand it back as well. So we had a control room on site. We were very lucky. We had Colton relay room right at the side of the track. It allowed us to set up a bit of a base station that we could get construction management and engineers set up with IT, and we could monitor exactly what was going on site. We also looked at right level of assurance. So we had some lessons learned between the blockades. So because we knew the criticality of the junction, we had increased tolerances on things like droppers. And between the blockades, we learned very quickly that trying to achieve that level of assurance was very hard. So we started to kind of focus down on what was actually critical, which droppers were the ones that needed to be right, which, you know, obviously saved us a lot of time on site. Progressive assurance. So we used EVIFAR through the whole stage of the build. So we were assuring as we were building everything that was going on out there digitally. We used SharePoint a lot on site as well. So we have pre-prepared documents out there. We're looking at things like electrical clearance checks, bridge clearance checks, dropper assurance, just to name a few. And those were actually being filled in live on site by the guys. We could sit in the control room and watch that coming in. So we knew, or we could see potentially any issues and get messages back out to the team so they could start to look at those. We also looked to get the Form E's prepared beforehand, so we could get those signed off on the night, no issues. You know, we agreed what wording will be in there. And lastly, we actually carried out the AMP16 walkouts as well right at the end of the session. So that gave a really good opportunity to get the maintainer out there, so they knew, you know, what the equipment looked like as we were handing that possession back. And then down in the bottom right hand side, you can see the very first train that came through in the morning. So handed back on time. Very good weekend, I think, on possession. A lot of stress gone from me. Okay, I'll hand you over to Luke.
Yeah. Mick.
Okay, obviously we've talked around sort of criticality of the junction and how, you know, it's a key piece of infrastructure for the East Coast Main Line and operational railway. So on hand back, we, you know, obviously going through that modelling process and kind of agreeing on a bespoke arrangement really, and you know, it's a one-off. So we wanted to have some mitigation in place for opening back up. To kind of mitigate any chance of potential defects or the system not running and performing as we predicted. So yeah, we following the week 52 works, we wanted to do this post commissioning monitoring, and we implemented a TSR of 90 mile an hour. So that was on the down leads for a week. And we went through a process of trying to think of how can we carry out this condition monitoring to determine that the OLE is functioning as we expect, and that pantograph interaction is as predicted, and the forces we're seeing are acceptable. So we actually went down the route of using digital image correlation to determine the level of contact wire vertical deflection or uplift. So we used a company called TRIS, and Nikos there helped us through the process. So we set up cameras within the SES, pointing at the kind of key locations within the junction where we saw the higher forces. And we had Martin on site as our local train spotter to let us know what was coming through the junction, what configuration it was in, what pantograph was it knuckle leading, knuckle trailing. And then we could compare that with the modelling that we did through the University of Huddersfield. And the measured uplift, when we compared it with the simulated values, was within sort of 5 mil of predicted. So we were comfortable at that point that we could lift the TSR. The next stage then was we wanted to run through the junction with the test train. Now the test train wasn't solely for the junction; it was for the new OLE that we were commissioning, the sort of 8 kilometres on each road through from Colton Junction down to Church Fendon. So there's a requirement within the NTSN for energy to carry out dynamic assurance with a test train if you're over 75 mile an hour. So we piggybacked really off the work that Midland Main Line had done with getting this the Class 91 unit, the sort of Franken train, I think Martin, if you refer to it. So we got that booked through Colas Rail, and then we ran the configuration of a Class 91 EMU with its panel, 2 Class 43 DMUs to get us up to speed, and then 3 Mark III coaches. So we ran that through the junction at 125 with an instrumented HSX pan. So we had Serco instrumented the pantograph for us, and then we could see the plot there. You can see on the at the bottom of the screen live on the train. So I think we probably had about 20 odd people on, didn't we? At one point, very interested in how it was looking through the junction. So I think, as Matt said, as Stuart said, we had kind of 180 at 9 newtons was predicted, and our F max through the junction was 201 newtons. So we were well within kind of the limits there. And that was going through at 125, so it was a little bit nervy on the train, but we didn't just go straight up to 125. It was a progressive, I think 30, 50, 75, 100, and then 125. So, but I think really, yeah, it kind of shows the accuracy of the modelling, the accuracy of the design, the installation, and obviously, and then the testing as well. So, a really good end to the whole process, really. And then just bolting onto this, just so it's not just all very technical on OLE. Talking about some MVP examples that we've, or minimum viable product examples that we've done on TRU East. So one of them is around a 72 metre span length. So this is pretty standard now for UKMS, increasing the span length. So we use fewer structures. E1's straight track, that's kind of where you can really only use those longer span lengths. And we've been top trumped, I think, by Midland Mainline with a 95 metre span. But yeah, so we're using 72 metres where we can. Very recently, we've done some lateral pile testing to reduce pile lengths in high rock areas. So we've been struggling to get foundations in on the route because of the high rock. So the geo team's done some, and the civil engineering team have done some really interesting work, sort of testing piles laterally, loading them up and seeing whether we can reduce the depth of foundations using a rock socket. So you can see that the graphs there with the lateral displacement and with the moment applied. So we're using the bottom graph there. You can see with a 4 metre pile with a 1 metre rock socket. We've got overturning moment like 350 with 25 mil deflection. So whereas compared to the top graph with just a 3 metre embedment depth, just over 225 kilonewton meter overturning moment with a lateral displacement for 25 as well. So it's just showing how much we can increase using the rock socket. And then probably one that Stuart was a lot more involved in was the review and analysis of the 610 pile steel boss and studs to allow an increase over the historical 181 kilonewton meter limit, removing the need for the pile caps and transfer plates. The use of voltage control clearances, so going down below the normal clearances that we used to have within standards. So the application of 27716, which is relatively new Network Rail standard. And then we're kind of in the process at the moment of drafting a regulation 14 against the Energy NTSN against clause 6.2.4.5, which is that testing clause that I talked about earlier, to try and get away from having to use a test train that's very expensive, to try and prove a system that we've built and assured already and used across the country. So yeah, that's going through at the moment, being drafted by the project, and then hopefully we'll be taking that with the support of the TA to submission to the ORR, so to try and get rid of that requirement. So, and I think that's pretty much everything that we've got. So I don't know if anybody's got any questions.
Yeah, actually, you know what? Well, I have one thing to correct. I have a couple of things I want to say. Firstly, thanks to the four of you. I'm going to say thanks to the four of you. There's a lot of information there, and plenty of acronyms for people to go through as well. SBS is small parts steel for any non-OLE people. But there are others. So a couple of things there that are really interesting. One of them is how much further ahead OLE are in business as usual for doing dynamic modelling. Like, it's something that in track world we just very rarely bother with. And actually we have quite a lot of complex, you know, whether it's junctions or just complex geometry, that we really ought to have a better idea of what trains are actually doing, rather than just shrugging our shoulders and go, well, it's kind of an anomaly within standard. And from Huddersfield do that as well. They don't just do the OLE modelling, they do the dynamic modelling under the wheels as well. And I kind of wanted to ask about that. I'm very, very glad you had a validation slide in. Talk about validating the work that has been done, because far too often the fancy stuff happens, you build it, and then you go, walked off. Has that now turned into some papers on the Huddersfield side? Have they actually then incorporate that into some?
They are doing, yeah. So we've handed over the test train results.
Yeah.
And they're at the minute, as we say, literally, they're overlaying it on the model is.
What perfect validation data they've now got.
Exactly, yeah.
Of,
So
incredibly complicated.
give us the data.
Yeah,
you know, so they're doing that, and they write the papers. Yeah. So they'll be publishing something.
Yeah, the other question, other questions were up, is I kind of, you jumped over the work that was done to justify needing to replace the existing layout. Can you just run again through what work was done to confirm why I absolutely believe that it was needed, but what work was done to just check that you needed to, you couldn't just sellotape onto the end of the overalls and crack on?
But I think it was it's a project that's happening here, and when's the next opportunity going to be able to do that? So it's an asset that we knew was going to be probably creaking at some point as well. So I think it's twin faceted, isn't it? There was a lot of concern that it wouldn't perform very well, and then we're in there. We've got the opportunity to do this work, albeit we lost a lot of that opportunity. So that when that decision was made, it was we're here. Let's get that resolved for the future. That junction.
Yeah.
Did we model it?
No. So we did have some. We did look at the data of the network rail test train, that was running up and down, that was giving forces higher than the 201. But obviously that was only running on the BCML. We didn't have anything that had gone across the other two routes.
The pandas thing.
Yeah.
So it's always running on the lower wire here. So with nothing 125 on the upper wire, sort of crashing through the lower wire with it cross contact.
It took a lot of kind of confidence to go and build that and then run a train at 125 miles an hour.
Any other questions?
Yeah.
Sorry, we'll follow it back and then,
Are there any lessons learned or are there any parts of the findings you have from this particular function that we can use in the future? I mean, yeah, this is a unique set of features that you probably won't find anywhere else in the country, but taking it separately, I mean, from the diamond switching, are there any things that we can use as an industry in other examples?
I don't know. I think the fact,
To think about.
yeah, the fact it is unique. I think the lessons we probably learned as a project would be,
From the modelling.
Yeah.
You've done so much modelling. Can it be taken and analysed individually to draw this would perform better, that would by doing this, it will improve what we have currently.
so I think it is bespoke Colton Junction. There is nothing like it at that speed. I think we've got another diamond junction at Micklefield, and that's 90 mile an hour in one direction, 75 mile an hour in the other. And we have implemented the Series 1 design that's been around for a long time because we don't deem the risk high enough, and we didn't feel like we could apply this learning because it is so bespoke.
It's a lot shorter as well.
Yeah, it wouldn't have, this wouldn't have fit.
You had to put an SI in that one, didn't you? Because it's slow speed, it's more compact junction, wasn't it?
You could maybe get rid of some of the things that we did try that didn't work.
Yeah, I think we'd know if we went into another modelling exercise, I think we'd get to the answer significantly quicker.
Yeah.
So you did
iterations
touch on it, Stuart, because you said if a turnout is a single direction,
Yeah,
there wasn't a need in the modelling for cross droppers.
yeah,
And that worked, and we knew that 2 years ago after week 35, when we'd done the first two turnouts, that cross droppers were not needed on a high speed unidirectional turnout.
Then we got a bit desperate as well halfway through. We were putting some sort of crazy ideas into the model as well. Weren't we? Try this, try that, try the other. But that kind of, at least it ruled out some things, didn't it? And just allowed us to focus on what we were actually needing to do. It was a learning curve for everyone, really, wasn't it? The uni guys as well. They could recommend. They were kind of saying that, this wire is moving too much. The rear pan's hitting it. You need to stiffen it up, but they didn't know how to do that with all the equipment, whereas we did. So they'd say you need to do this, and Stuart and the guys work a solution out.
Follow-up question for that. So let's say if I'm senior early design engineer and reading the UK investment book, how would I know if the cross dropper is going to work or not? When I would feel like modeling is needed. How did you get to this point where you started?
but in only half cross droppers rather than both. Through the modelling process, I think if you've got discrete features like a turnout and crossover, I think the modelling that's been done and the general agents that have been produced are probably suitable.
Yeah.
Are they risk averse? Probably, but does that make it a bad design? Is it significant additional work to put cross droppers, set cross droppers on both leading and trailing crossovers? Probably not. So I think it'd be where we identify something as at significant risk of high forces, where you go through this
High speeds and
The key area
significant
was
features after each other, isn't it?
switch diamond and tangentially wiring, switch diamond.
They're all mainland wires.
Question, yeah,
Yeah, I want to go back to the pantograph configurations that you looked into. And I'm going to pick up a particular one, just as an example. The double-headed freight, the pans were 8 meters apart. And you looked at it, very high forces on the overhead line, but it didn't run. So didn't really have to take that into consideration. Two-part question then. 10, 20 years time, what's to actually stop them running that? And B, if they do, what's the risk?
I think you'd have to really carry out some modelling. However, we know what is there. Obviously, if you were to introduce a new set of rolling stock that's not on the statement of compatibility or special appendices, then stuff has to be considered. As vehicle gauging or anything, this would need to be considered now as an asset.
So the sectional appendix was saying you couldn't run a double-headed freight through.
Exactly.
Okay, that's the answer then. Thank you. Yeah.
Well, a modern electric locomotive probably has some built-in power to old classic 86s or something.
but they can get the power down.
So, yeah.
20 years time, they'll say, let's go for 2 litre locomotive.
I was going to say, if you look at the two, well, which had a very interesting presentation on this from Freightliners saying that you will always struggle to get you can get the power out of the single vehicle, but you just really struggle to get the mass in a single loco. So you're likely that it's going to be a long time. Yeah, it's basically like the physics question is you're probably just going to see a Oco or Bobo, etc. But even then, it's still that mass. It's the mass question. So yeah, it's interesting that has been ruled out, given it's probably going to be the way that we'll see more electric freight moving up that. With far too many 66s going through Colton Junction, and that won't last that much longer.
But the point is, it's recorded in the sectional appendix.
Yes. Yeah.
I think if you reran the model now with that configuration, it performs significantly better than it did in that first bit as well.
Good question. Please.
The constraint runs on these codes, how does that run?
So
it's a project, or is it sort of a regular?
No, it's that moment we I had the test train purely for commissioning of the new OLE testing. Yeah, but there is mentor, isn't there, that runs up that it wouldn't do.
Yeah, it's an instrumented pantograph mentor. They're looking at instrumented in service passenger trains, aren't they?
Yeah.
And there's the PANDAS unit as well, which is on quite a few trains, isn't it?
Yeah.
But that just gives you an alarm. It senses a high force on the pantograph, high acceleration. Yeah, it doesn't give you these traces.
It can warn you if not.
Yeah.
Yeah, so we had the asset engineering team were monitoring that, weren't they? After we.
Yeah, when we opened it up at 90 initially.
Yeah.
So we did the uplift measurements that correlated to the model. But we also had pandas units going through as well. And no news was good news. There's no alarms being set up. So
Are you going to put your regular data? Is it weekly or daily? Mentor and possible run the whole network. And mentor gives you this kind of right? Yeah, which got to be done. And then he also runs which one's like so you can say they're only when you see on it, you also try to get a trace, only go get a similar. Yeah, I just I get it.
Mentors not 120. It's not 195, so you're not getting the full down ones. Yeah, this is why it'd be good to get it in service trains, I suppose, isn't it? So you get that.
Yeah.
Regularity.
When was transferring down, it's all about that. And they're working on getting standards from companies. I'm looking at where the wire is and trying to get that better measurements.
So it's the sort of thing that you want to get plugged into Insight. We've got, I think, never else.
There is some, there won't be a recent update about on Insight which had better acceleration for early. Yeah.
Okay, yeah. Insight is we'll have an update about Insight next year, I'm sure, in Yorkshire PWI, but a very interesting bit of work. Ben.
Just an observation, team on the Midland Main Line that are upgrading the OLE to 12125 south of Bedford have now just taken that through going into service without the need to run a test train to demonstrate being suitable for
Sure.
employees. So definitely,
Yeah.
I'm guessing you join the
Yes.
but they're
Science we've had in Leeds talking about this very thing. It was the aim, wasn't it, to say
Yeah.
we don't need to do
And I
this.
think 5 decarbonisation projects are just going through that as well. So we're using their application, to be fair, as a template for.
Than their rec 14.
Yeah, so, no, it's yeah, thanks, Ben. It's good to see this, kind of alluding to other questions I've had, it's good to see this cross learning. You know, I admit that it's right at point when the government's decided to just not electrify anything more, but anyway, but it is extremely good to see this learning being, you know, some of the things we've heard being talked about in our, you know, in our section last year off Little Main Line, and seeing those bouncing around is really, it's good stuff. There was once a similar observation, which is related to construction, and this again runs across disciplines, is how critical it is to ensure that the teams who, as you say, aren't getting a full suite of GAs and 6 months or more of meetings and understand why, if they understand why they're being asked to be careful on installing, you know, particularly picky on certain elements, not just like, oh no, we have to do it because we've been told to, but oh yeah, because this is, you know, there's no one out there who's not fully a clever person to understand what's going on. So it's kind of, as you say, it's informing them as to this is the really important bit of the dynamic. You can see why we have to be really careful on these bits. That just feels like a really important message that has come out of this, is get the team building this stuff up to, you know, in the loop on that process, and why the designers and the construction CREs wanted to be specific on that point.
Yeah, absolutely. I think, well, for me as a construction CRE, getting involved, we were sat in some of the modelling meetings as well, which, you know, we never get to understand what's actually going on. And it allowed us to kind of filter the message to the construction teams about exactly why we needed these tight tolerances. Obviously, you know, we know what linesmen are like. It was hammering the message hard home that everything had to be absolutely to, you know, we're asking for 10mm tolerances on droppers, which we
For out of the front tie-ins that they need to be,
absolutely, yeah. So, and you know, everyone bought into that. And yeah, it was just really robust briefings. We took supervisors out in the weeks leading up, walked them through the design, answered all their questions, then we let them build presentations to individual shifts so they could kind of explain to the guys on site exactly, you know, what they were doing in the shift and what the critical bits were they were looking at.
Yeah, just really strong. It's not just TRU to be doing this, but certainly when I was designing, I was seeing that much closer working between design and construction CREs that would then cascade out, was just really important. As a designer, you're flying blind in a way. You kind of want that. Certainly when I was designing, I want that. I want to speak to the team who built it and then also maintains it. So yeah, really good message.
We had that support on site as well, so it wasn't just left to construction. So we had design team came out on site with us through those weekends as well. The PEs were out through those weekends, so you know, any little issues we had people to fall back on as well. Really good.
Really good. Who's driving online? Are there any questions coming through online? Oh, there's a question about it.
Sorry, just looking forward, is there any special, you know, like, is this maintenance intensive, or is it going to be getting new building and other things? Is it so like it's because it's obviously very carefully used. Does it need extra sort of?
Does it have like green blocks equivalent or something like that?
No, we obviously brought the technical authority along the journey with us, and where we got to with the refined design and hand profile and the forces, you know, we're happy you can just use standard UK Master Series maintenance principles and tolerances, especially with, you know, the forces we were ultimately seeing, which is they're just like normal ordinary values, to be honest. But that's sort of clearly sort of stated on all the as-built documents we're handing over to maintenance.
Oh yeah, question that.
What's the tolerances? I actually can't remember how the droppers of battery. What's the tolerances on if it's doing to demarcations if it's slipped? 5 mil, 10 mil.
It's 5 mil junction area.
5 or 10.
5 mil
Yeah.
junction area, which is this as per MS anyway. Yeah.
I think we went down that route as well, didn't we? Defect rectification, you know, what cross-tracker coming off, and we're looking at that, aren't we, as well, with the TA?
We are, yeah. Yeah, clarifying that.
Any other questions, or shall I wrap up? That was absolutely superb. And before we shout some more, I'm just going to ask Ben to come up and say things. And I've got a few announcements after, so don't run off too rapidly. I have a couple of things to say, but Ben, I'll let you go first.
I was going to have
Confident
a
a
quick
bit and-
plug. So I think most people know me anyway, but Ben Brooks, Vice President for PWI in Yorkshire and the North East. Couple of things. While I remember, I've been talking to Sheffield University, Leeds University and Huddersfield about having a university postgrad themed evening on our 2026 programme. I think we've got a March date sorted, so all three universities have come along and give a bit of a presentation on something that they're interested in sharing with us. So that's good. I just wanted to highlight PWI from a membership perspective for anyone in the room that isn't a member. That was my shameless plug at the end of the meeting. So firstly, just to remind everyone that we're an institution that is called a permanent way institution, but we are by no means track dominated and entirely track focused. We're also not just an organisation for engineers. The focus really is around people involved in delivering railway engineering rather than people that are specifically engineers. Feedback from members and also feedback from broader industry very clearly says the name is confusing. So for anyone that is a PWI member by November this year, you are likely to be involved in a members vote around what the institution is called. And the proposition is the Railway Engineering Institution rather than the PWI. So if you want to be part of that and want a chance to have your say on that, then get your membership sorted over the coming weeks and months. In addition to the local meetings example shown here, there's also a quarterly journal, not an online knowledge hub, which is you've got all of the talks delivered across all of the various sections nationally for however long we've been putting them online. And you can also become professionally registered with the PWI right to chartership level, not just in track. So it offers that development opportunity as well. Free for apprentices, reduced price if you are of a retirement age, and if you're not none of those, then you'll probably persuade your employer to pay for it anyway. And if they can't because you're already paying for something else, it's less than £10 a month. So there we go. I'm getting quite practiced at that.
Yeah, that's fine.
Now you can pay monthly.
You can pay monthly at £9.90 a month or whatever it is. So it's minimal, and you get a whole load for it, and you get to be part of that decision around are we the Railway Engineering Institution or the PWI.
Which Ben's very magnanimous is the right word. You're very anyway, basically I take a different time, which is we absolutely should be changing our name. I strongly advise everyone to support that decision because it's a name that actually the public might understand. And it doesn't get rid of the legacy. That legacy is still there. We can be extremely proud of it. But it just shows that we're, this presentation is not us thinking it's polite to let all the engineers through the door once or twice. This is an inherent part of what we do as an institution focused around rail engineering. And that gets me very excited. I don't know why I'm sat down in the back corner like a weirdo. To the front, we will say a proper thank you again at the end, but that was absolutely brilliant. Thank you, Ben. We have some committee roles that I want to plug. We will be being more specific about what titles of committee members there will be next year so that we understand where we have gaps and where we need people to be involved. Look out for an email from me, a round robin from me, going through what that structure is going to look like over the next couple of months, particularly for West Yorkshire and South Yorkshire. We want to continue having involvement across all of Yorkshire, not just focused on York. But to do that, we need people, and online, hello everyone online as well, we need people from those areas to get involved. TRU being a key part of the West Yorkshire activity, come and get stuck in. We have got quite a range of different bits and pieces coming up. So the next York session is on the 21st of August, is about Brownie Curve, which should be very, very interesting indeed. On the 2nd of September, this gentleman who's just been speaking is speaking in Leeds, I believe, is the date. Ben is coming in and talking about sustainable thinking in projects. It's right.
Okay, good.
That is right.
It was suggesting that might get moved back, so I'm really.
Oh, it might be slipping because of holiday time of like landing on things. So pay attention to the date updates on that one, but it's the next Leeds meeting and you'll be updated on when that is. That'll come through in your automatic emails as well. It's from my brand, Robin. And we also have a site visit. Here. Pandle site visit. Do we have a date confirmation on that yet? Or
last week of September, we're looking.
Last week of September will be a Pandle site visit. So if you want to see where Pandle clips get made, among 150 million other things, then that should be very, very interesting indeed. And of course, on the 1st of October is the North East Rail Engineers Forum, which is there's a lot of TRU stuff there because that's all that's going on up here at the moment. Except there isn't, because we're also talking about Nexus and Tyne Metro new fleet stuff, which is very exciting indeed. That's enough of my waffling. It's been an absolute delight to have you all here. And can we just say an absolute thank you to the crew of four. I think one of the best staff that I've in a while. Thank you so much. Everyone online, thank you so much as well. Have a very good night. Yeah, cheers everyone. We'll reset the room. Get comfy. Thanks to everyone who's come along, who doesn't normally come along. Oh yeah, pub. Those online, you're stuck, I'm afraid. But everyone here, we're going to go down to the station tap for one or two halves. These all of you must come along unless you are going to disappear for travel reasons. But it'd be nice to have I take it you're on the train, or I don't know if a couple of years are here anyway. So yeah. No, thanks so much for that. That's really, really good. It's not, again, I always despair. Two things. Track engineering on my side. It's always this slide. So rarely do we get to go, oh, we've done all this fancy stuff. We're not assessing that it was at work, so whether it's alignment or whether it's aging solution, whatever. And then also the dynamics at all. It's the thing with track is one of the reasons I hated SDs. It was a laying, not only was it scientific, pseudo-scientific rubbish, but also if you're familiar with SDs, it's our way of doing the dynamic model, going, well, there's not too much going on at once. It's based on pseudoscience. We don't do enough modeling checking. It's not this way, that way, exciting. And we all basically hide behind 2 seconds, and that was all we do. But yeah, no, thanks. That's really, really good. Yeah, nice. Oh. Yeah, I enjoyed it. It's both the two projects. Construction theories I was working with.